Okay, so let's get started. Well, as a reminder, you have an exam Thursday in class. And so this is mostly going to be a review session for that exam. Just like the last exam, the exam is only an hour long, so it doesn't take the whole class period. It'll start a little bit after the start of class, but do try to get there on time so you have your full hour to work on the exam. More generally, the review materials are online. So if you go to the website, to the Canvas page, you'll see a link. It's been up for a while now, but you'll see the link to the exam one sort of template and study, or exam two template and study, which sort of shows the format of the exam. It looks a lot like exam one and the types of questions that will be on it and any additional rules. But the rules are basically the same as they were for exam one. So for example, you're allowed to have one page front and back of notes, but no calculator, and so on. Good. So yeah, for the review session today, we're just going to go over some examples of the types of problems that might be on the exam. And then after that, I'll have time for any specific questions at the end. I'll ask also, feel free to interrupt if you have questions as we go over things. And so the video is being recorded and I will post it right afterwards. I will also post the solutions to the homework that you guys turned in last night. So I'll post those right after this video. Okay, so let's get started. So the first problem, just like on the last exam, will be some very short answer questions. So these are asking you you don't need to give any justification on these. Last time there were 20 problems. This time there are only 10 problems. They're still worth 1 point each. And so, for example, you might have to compute phi of n for some number n. So you should know how to compute phi of n. Using the prime factorization and then computing phi of prime powers. So you should know sort of those rules that let you quickly compute phi of n. If you don't know those rules, go back and look at the slides from the lecture where we introduced this Euler's phi function. For example, you should know the conditions for the Chinese remainder theorem to apply. You should know the conditions for Hensel's lemma to apply. You should know basic facts about primitive roots, like when they exist, when they don't exist, sort of different characterizations of primitive roots, etc. So this kind of thing. And again, if you go back and look at what kinds of questions were asked in the first very short answer question, then you sort of can get a good idea of what type of questions you might be expected. Some of them will involve making a short computation, like on scratch paper. Some of them you should just be able to say right away, yes or no, if you know it, or sort of if you look back on your note page, maybe you've written it there. So they sort of vary in sort of length and difficulty, but all of them, you don't need to write a justification. You just sort of give a short answer. Are there any questions about this? Again, it's very similar to last time, just there are half as many problems this time. I'll give a minute in case anyone's typing a question. I'm at an Airbnb, so I have unusual background. There's a cool poster behind me. Okay, well, let's move on to the next thing then, if there are no questions. Okay, so after those very short answer questions, there are 4 problems. So each problem 2, problem 3, problem 4, and problem 5. Make sure you look at the back of the exams. So make sure you do all 4 exams and all 4 problems. 1 or 2 people sort of forgot to do the problem that was on the back of the exam last time. So just make sure you sort of look at the back page before you turn it in. Good, but so each of those 4 problems is worth 10 points, and these are sort of more computational problems. These are sort of more computational problems, sort of illustrating that you know how to use the basic computational techniques we've introduced since the last exam. So let's go over these. So problem 2, which is worth, again, 10. All of these are worth 10 points. You're supposed to solve a linear congruence modulo prime numbers, then put together your results using the Chinese remainder theorem to solve it modulo a composite number. So for example, I want to solve 3x plus 2 is, this is not a problem, sorry. 3x plus 2 is congruent to, let's say, 5 mod 91. So I want to solve this linear congruence modulo the composite number 91. To do that, sort of as instructed by the problem, I should sort of first solve it modulo the prime numbers 7 and 13 that appear in the prime factorization of 91, and then sort of use the Chinese remainder theorem to put those together in order to solve it modulo 91. So let's do that. By the way, on the exam, like if I sort of tell you to solve something modulo 91, I will tell you like 91 is 7 times 13. I'm not expecting you to sort of have sort of that memorized or sort of be able to sort of factorize into prime numbers on the fly. So good. Okay, so I'm solving 3x plus 2 is congruent to 5 modulo 91. So first solve it mod 7 and mod 13. So first I solve 3x plus 2 is congruent to 5 mod 7. So that's 3x is congruent to 3 mod 7. So x is congruent to 1 mod 7. So I just subtracted off this 2 from the 5. I got x is congruent to 1 mod 7. So I sort of set this up. So it would be easy. On the exam, you might have sort of a harder one to solve. Like once you got here, maybe like there won't have 3 here, like maybe we have 4 here. So you'd have to do more work to solve this, but I just wanted to have an easy one for the example. And then I'm looking at 3x plus 2 is congruent to 5 mod 13. So again, I get 3x is congruent to 3 mod 13. I get x is congruent to 1 mod 13. Sorry, I get x is, okay, good. So I'm looking for x is congruent to 1 mod 7 and x is congruent to 1 mod 13. So of course, I mean, it's pretty easy to see what the solution actually is. The solution is just x is equal to 1 mod 91. And sort of somehow I could have done that from the start. But the point is, like in this problem, you'll actually be asked to use this method using the solving modulo prime numbers and then sort of putting together the Chinese remainder theorem. So let's sort of go ahead and remind how we do that. So once you put it together with the Chinese remainder theorem, first we sort of do the following. So our solution should be x is going to be equal to so first we do do these n over ni's and sort of so on, so you can go back and review the Chinese remainder theorem. So like the first thing we do is we do some multiple of 13. So 1 plus so 1 times something times 13. So this is to get something that's 1 mod 7 and 0 mod 13. And the thing you put here is sort of the inverse of 13 mod 7. And then the thing you put here, and then you sort of do again sort of. So here we're trying to get, now this second term is going to be something that's sort of 0 mod 7, but 1 mod 13. So sort of this 1 comes from this one, and so this one came from this one. Then sort of something here, and then here we'll put 7. So this is the inverse of 7 mod 13. Okay, and so if I do that, well, I have 1 times what's the inverse of 13 mod 7? I can take that to be -1. So -1. Yeah, so 13 mod 7 is sort of 6 mod 7, so sort of -1 6 is -1, and so -1 is the inverse. So for example, I could take this, write this to be -1, or I could write it to be 6 if I wanted to do a positive number for the inverse. Either would be fine. Let me do it as a 6 because that's sort of what we did before. So 6 is the inverse of 13 mod 7 plus then the inverse of 7 mod 13, again, sort of, and you can write out the equations if you need to solve this. Like, so I'd be like solving 7 times x is congruent to 1 mod 13 to find the inverse of 7 mod 13. Here I can, or you can just sort of eyeball it if you're able to. So here, like 2 times 7 is 1 mod 13. So 2 is the inverse of a 7 mod 13. So plus 1 times 2 times 7. Good. And so this is mod 91. So I get x is, so 6 times 13, that is 78. So that's 60 plus 18. So that's 78 plus, here I get 14. That's congruent to 92. So 78 plus 14, that's 88 plus 4, so it's 92. And this is congruent to 1 mod 91. Good, so that, and so like I said, we got the answer 1. On your exam, the answer will not just be 1. But it won't be too much harder than this to solve. So like this step might be a little bit harder on your exam. It won't be much harder, where you sort of solve mod 7 and mod 13 or mod whatever prime numbers show up. And then sort of, so this step might be a little bit harder, but not much harder on the exam. And then after you sort of finish that step and you put them together, the solution mod 1 prime and the solution mod another prime using the Chinese remainder theorem. So it looks exactly like this. So review the Chinese remainder theorem and how that works. In the end, you'll get something like about the level of complexity of sort of this to compute, and then you'll put that together and you'll get whatever you get, mod whatever n is in the actual problem, and that will be your answer. One thing I want to point out is you should be comfortable multiplying like 2-digit numbers with each other. So if you're rusty multiplying 2-digit numbers, I mean, maybe just sort of do a little practicing, but someone feel free. I mean, on the exam, like you have an entire page to write out this problem. Like in the end, you might need to multiply, like when you're sort of doing this step, like you might need to multiply like some 2-digit numbers. So if you're worried you're going to get the wrong answer, if you do 6 times 13 in your head, for example, like you could write out 13 times 6 using sort of like this sort of long multiplication. So somehow, and you feel free to write out and expand these things carefully to make sure you get the right answer. You will be expected to sort of make computations like about as difficult as like 6 times 13, or even on the last problem, maybe like a little bit more difficult than that. So just, and you should have plenty of time to do those computations. So just take your time to do those right on the exam. Someone in the chat asked, will the composite mod only be a factor of 2 primes on the exam? Yes, on this problem, on problem 2, it's going to be just like this. So you'll be modulo a composite number that's a product of just 2 primes. So it'll be very similar to this. You should know possibly for like the short answer questions. So the very short answer questions like problem 1, or maybe if it shows up, I don't think it shows up anywhere else, but you should know how to do this Chinese remainder theorem for more than one, when there's more than one factor. But for this problem, it's only going to show up with sort of a composite number of 2 factors. Did that answer the question? Okay, great. Are there any other questions about this problem? Okay, great. So yeah, so just then to highlight, so for this problem, you want to review solving congruences modulo prime numbers. So solving linear congruences modulo prime numbers. And you want to review sort of how to do the Chinese remainder theorem. especially for sort of combining sort of the solution modulo of two prime numbers to give the solution modulo their product. And if you're comfortable with those two things and sort of multiplying two-digit numbers, then you should be in good shape to do this problem. Okay, so we'll move on to the next one. So we want to solve a polynomial congruence modulo at power of a prime number using Hensel's lemma. Here's an example. Let's find a solution to x cubed plus x plus 3. Sorry, I sort of forgot to write the right-hand side of all my equal signs here. So this is supposed to be congruent to 0. Sorry. There we go. Congruent to 0 mod 343. 343 is 7 cubed. Okay, so I want to solve the polynomial congruence modulo a power of a prime number using Hensel's lemma. Note this is not asking me to find all of the solutions, it just asks me to find a single solution. So I don't need to sort of like exhaustively check that I find all of the roots. I just need to sort of check how to find a single root. So in this example, and you should know the difference between those two because the problem the actual problem, maybe it will ask you to find all of the solutions, maybe it will only ask you to find one of the solutions. So you should know the difference. But here I'm only being asked to find one of the solutions in this example. So how do I do it? Sort of step one, I need to find a root or a solution mod 7. And I should do that by guess and check. Okay, so if I do, so I just start plugging in values. So 0 cubed plus 0. So if I plug in x equals 0, I get 0 cubed plus 0 plus 3. That's congruent to 3, not 0 mod 7. Okay, so that's not a solution. 1 cubed plus 1 plus 3, that's congruent to 5, which is not congruent to 0 mod 7. If I do 2 cubed plus 2 plus 3, that's congruent to 13, which is not 0 mod 7. If I do 3 cubed plus 3 plus 3, that's 33, which is not congruent to 0 mod 7. If I do 4 cubed plus, so yeah, maybe I should start doing minus numbers now instead of, because it's sort of hard to cube 4. So if I do minus 3 cubed plus 3, so plus minus 3 plus 3, now I'm getting, so minus 3 cubed, that's minus 27, minus 3, that's minus 30. So, plus, oh yeah, so this is minus 27, this is not 0 mod 7. Okay, let's do minus 2 cubed minus 2 plus 3. So that's minus 8 minus 10. So minus 8 from this minus 2 cubed. Minus 2 is now minus 10 plus 3. This is minus 7. So that is 0 mod 7. So I found a root. So minus 2, or as a root mod 7. I like working with positive numbers, so let me write that as 5 instead. So 5 is a root mod 7. Good. I mean, you could do everything working with minus 2 as your initial root mod 7. I just like working with positive numbers. So that's why I don't have to keep track of like all these negative signs. So 5 is a root mod 7. And now I have to sort of lift this. So I have to use Hensel's lemma to lift. So I should check. I have to compute sort of the derivative of x of f at x. So f prime is 3x squared plus 1. So f prime of 5 is 76, which is congruent to, well, I can subtract, like if I'm working, so 76 is 3 times 25. So x squared is 5 squared is 25. 3 times that is 75 plus 1, I get 76. 76 is congruent to 6 mod 7, which is, I can even write as sort of minus 1 mod 7. That'll be useful in a second. So this is non-zero, so sort of Hensel's lemma is going to apply. So let's look at that. In fact, maybe I should, well, sorry, I started doing this. Maybe I will leave it as -2 actually instead of 5. You could do this with 5 too, but you're going to get some sort of bigger numbers. So let me sort of start with -2 actually as my initial value. So if I do f prime of -2, I'm going to get the same thing mod 7, but let me write out the actual computation. So if I do f prime of -2, mod 7, so I get 3 times 4, so I get 13, which is congruent to 1 mod 7. Okay. So again, so I mean, this is sort of actually maybe a helpful thing to point out just for using Hensel's lemma in general. I mean, you can, I mean, somehow like you're free to use the least absolute solution instead of like the least positive solution. And like sometimes that will end up giving you sort of smaller numbers to work with. Like for example, like when we do Hensel's lemma, we're going to need to know like what f of -2 actually is, because then we have to sort of divide that by 7. Here, f of -2 is -7, whereas f of 5 is sort of going to be like 130, like 133. So somehow it's a little bit easier to use -7 than 133 in the next step. Okay. You could use either, and in the end, like in the end, you'll be fine. You're going to get sort of the same answer in the end, but somehow it can simplify some of the computations if you make better choices at the start. Okay, so anyway, so some of the point is, so this is supposed to be congruent to -1 mod 7. The point is, the derivative is not 0, so the derivative of my sort of root mod 7 is not 0 mod 7. In other words, it's a simple root mod 7. So I can apply Hensel's lemma to lift it to a root mod 7 squared. So mod 7 squared, I get the solution. So I -2 plus k times 7, where k is a solution. Whoops. Sorry, I guess it's just crashed. Hopefully I didn't lose. I was just writing. Okay, didn't lose too much. Let me try that again. So my solution is going to be x, so mod 7 squared. My solution is going to be -2 plus k times 7, where k solves f of -2 over 7 plus k times f prime of x is congruent to, so k times f prime of -2 is congruent to 0 mod 7. Okay, and so, well, we know what these values are. We know what f of -2 is, and we know what f prime of -2 is. So f of -2, this is -7. So when divided by 7, I just get -1 plus k times f prime of -2 is also -1. So I'm going to get, once I solve that, k should be equal to -1. Okay, and so then my solution is going to be minus, so x is equal to -9. So that's going to be my solution mod, that's going to be my solution mod 7 squared. So that's -9 mod 70 squared. Mod 7 squared, I can also write that as 40 mod 7 squared. So 7 squared is 49. Good. And so okay, that's my answer mod 7 squared. I still have to do one more step, right? I still have to lift it to a solution mod 7 cubed. I'm not going to go through that here in the interest of time, but you would just repeat sort of the same step. So you'd have to do, you'd have to compute sort of -9 cubed plus -9 plus 3. So you'd sort of do that. You'd have to divide that by 49, so 7 squared. So that's a little bit more complicated than like anything I'll ask you to do on the exam, but like you could do that by hand. And then you'll sort of get the solution here. Good, and then you have to compute sort of the derivative here, but sort of the derivative actually, and this equation you're solving to go up from 7 squared to 7 cubed, it's the same sort of somehow. So like you still get actually just f prime of -2 here. And okay, so you'll be able to do this. So if you go back over your homework, you'll see some examples where you did this. But that's the idea. Good. So somehow, anyway, this would be my answer. So 40 would be my answer if I was sort of computing at mod 7 squared. You have to do some work to sort of go up to 7 cubed still. So on the exam, the power will be no higher than 3. So the power of the prime that appears will be no higher than 3. If it is 3, it'll be set up so that the numbers are work out pretty nicely, so that the sort of this last step where you sort of have some 3-digit numbers appearing ends up being pretty simple, like all of the arithmetic. Or it will be set up so that, or this will just be a 2, in which case something like you'll only have to go up, do Hensel's lemma once. So to sort of go up to 3, you have to do Hensel's lemma twice. But if it's a third power appearing, then you'll have it'll be set up so the numbers work out nicely. Are there questions about that or about this problem? Should we come with the first 12 numbers cubed? No, you don't need to come with the first 12 numbers cubed because, yeah, thanks for the question. Because like, for example, like if I ask you to solve, like find a solution mod 7 cubed, I'll sort of tell you that 7 cubed is 343. The next question someone asked is guess and check the best strategy to find the first solution step 1? Yeah, so somehow like guess and check is actually basically the only strategy you can use to find a first solution. I mean, I guess like if it's a quadratic, and there is a cubic formula, but somehow like the cubic formula is more would be more work to use than just guess and check. And plus you'd have to like know the cubic formula, which is sort of much more complicated than the quadratic formula. If this were a cubic, I mean, I haven't sort of told you what power, I'll tell you the power appearing, like the power won't be bigger than 4, let's say, like the degree of the polynomial won't be bigger than 4 on the actual exam. But somehow, I mean, the same strategy works for any power, and like actually for any polynomial of any degree, and no matter how big the degree is, like all these things you can sort of compute pretty easily still, because it's easy to compute powers like modulo a prime. The primes appearing won't be too big, and so the prime that appears will be 13 or smaller, let's say. But yeah, so somehow guess and check is basically the only strategy you have to find the first solution. This is the solution mod the prime. Are there any other questions about that? And let me just, in case I guess someone's reviewing slides, just right, you need to let me just write down that we need to do a little bit more to get to the solution mod 7 cubed. Well, if f prime is minus, so if the derivative is 0 mod 7, it's not that there's no solution, it's that Hensel's lemma doesn't apply. So someone asked if the derivative had been 0 mod 7, then is there no solution? And that's not the case. So if the derivative is 0 mod 7, then this sort of equation definitely has no solution. But it may be the case that there is still a root of this mod 7 or mod 7 squared or mod 7 cubed. So we saw a few examples of this actually, if you go back and look in the slides when we first talked about this kind of problem. And in that case, like basically your only strategy is to still guess and check mod 7 squared. But that's not going to happen in this problem because this problem, I mean, I'm telling you now you're going to have to use Hensel's lemma in this problem. So when you do this, like you should sort of find a root where Hensel's lemma does apply. So if you sort of find a root where the derivative is 0 mod 7, you should go find a different root instead. Does that answer your question? Okay, great. Good. Well, let's move on then to problem 4. So problem 4 asks you to find a primitive root and solve a congruence using it. So this will be something like the congruences in chapter 10, exercises 15 through 19. So these are sort of like, in class we saw like these two basic type of congruence problems. One of them sort of look like this. So here's an example that we'll do right now. X to 11 is congruent to 5 mod 18, or like 11 to the y is congruent to 7 mod 18. So a congruence where either you have like a power of something, or you're sort of solving for the exponent. These two types of problems. And for both of these, like if you have a primitive root, you're in good shape. Okay, so let's find a primitive root mod 18. Sort of, let me just maybe add a note. So 18 is 2 times 3 squared. So we know there is a primitive root. So if you go back and look at the result we discussed and even basically justified in the video, in one of the videos, there's a primitive root mod n exactly when n is 2 for a power of a prime number, or a power of an odd prime number, or 2 times the power of an odd prime number. So here we're 2 times the power of 3. So there is a primitive root. Okay, and so, well, but for finding a primitive root, we just do guess and check. So first we write down sort of what are all my candidates, and then I sort of just look at them until I find one that's a primitive root. So let's compute u of 18. Well, so I want to know what are the units mod 18 in order to find a primitive root. So those will be all the numbers co-prime to 18. When you're computing sort of what the group of units is, it's sort of helpful always to sort of first write down what phi is, because that's going to be the number of things. And so phi of 18, well, this is going to be phi of 2 times phi of 3 squared. So phi of 2 is 1. And phi of 3 squared is 3 squared minus 3. So this is 6. So we know there are going to be 16 things in the units mod 18. And we can just write them down. So right now, all the co-prime numbers 18. 1 is co-prime to 18. 2 is not. 3 is not. 4 is not. Then 5 is. 6 is not. 6 is not. 7 is co-prime to 18. 8 is not. 9 is not. Shares a factor of 3. Shares the things that, like, anything that's divisible by 2 or 3 is not co-prime to 18 is the point. So 7 is not, or sorry, 7 is, 8 is not, 9 is not, 10 is not, 11 is, and then 12 is not, 13 is, and then the last one is 17. Here's a good trick for this, by the way. I mean, so if I look at these, I sort of did 1, 5, and 7, I found just by sort of going through and checking in my head, like which ones had common factors of 18. And these are the only ones that didn't have like any common factors of 18. And then, but once I get sort of halfway up, so once I get half of them, then the other ones are just going to be minus these ones. So like 11 is minus 7 mod 18. 5 is, 13 is minus 5 mod 18. And 17 is minus 1 mod 18. So when you're writing that down, that's a little trick you can use that makes it faster. You don't have to use that, and you can just sort of go through all the numbers and check which ones have a common factor with 18, and sort of write the ones that don't. Because again, sort of this U18 sort of the units mod 18, which is the same as saying that things have GCD1 with 18. So no common factor except 1. Okay, so that's sort of the unit group U18. Its size is 6. And we want to find a primitive root. So we're looking for something whose powers, it's like we're looking for one of these guys such that every other one of these is sort of a power of it mod 18. But we know a criterion, like we only have to check a few powers and see that they're not 1 in order to get this. So here to check if A is a primitive root, let me say it this way, A in U18 is a primitive root exactly when A squared is not 1 mod 18 and A cubed is not 1 mod 18. So that's coming sort of, so this 2 is coming from taking 6 and dividing by 3, and this 3 is coming from taking 6 and dividing by 2. So the 6, this is the order of the unit group, and we know, so this is this sort of, in this lecture we talked about primitive roots the day before we did cryptography. What we sort of culminated with, sort of the final criterion that we ended up using as the most efficient one to find primitive roots was this criterion that you only need to check the powers of A given by sort of taking phi of n, so the 6 here, the size of the unit group, and dividing by each of its prime factors. So the prime factors of 6 are 3 and 2, so I just need to check 6 over 3 and the 6 over 2 power, so the second and third power, and you check those aren't 1, and if I have any number where sort of those aren't 1, mod 18, then that number is going to be a primitive root. Okay, so I just need to apply that. Good. So good. So I have my candidates. Well, 1 is never going to be a primitive root. And so 1 squared is going to be 1 in this case, so that's no good. So the first thing I should check is 5. So I should look and see, does 5 satisfy this? Okay, well, 5 squared is congruent to 25, it's congruent to 7 mod 18. Good. So then 5 cubed, well, that's 5 times 5 squared. So that's 5 times, since 5 squared is 7, that's 5 times 7, which is 35. And that's 17 mod 18. Okay, neither of those are 1 mod 18. So 5 is a primitive root. So that's sort of the idea. I mean, sort of, I have 5 squared is not 1 and 5 cubed is not 1. So without sort of computing any more powers, I know that it's a primitive root. So good. So this is sort of answers the first part of the problem. I found a primitive root mod 18. If I had encountered, like if I did this, and I got like 5 squared was equal to 1 mod 18, or I got 5 cubed was equal to 1 mod 18, then that would mean 5 was not a primitive root, and I would sort of move on to the next thing. So that if I found 5 was not a primitive root, then I would just try 7. And if I found that was also not a primitive root, then I would just try 11, and so on. So you just sort of start at the smallest and sort of just go up, trying them until you find one that is a primitive root using this criteria. So that's how you find a primitive root. Good. So I have this primitive root, and now I need to solve this equation. X11 is congruent to 5 mod 18, and 11y is congruent to 7 mod 18. So let me make a new page for this. So here 5 is my primitive root. And if you remember back on your homework, when you're doing this, it's really convenient if you first just write out all of the powers of 5 mod 18. So you sort of give yourself like a little logarithm exponential table. So here I should have x, and like, let me say it this way, the exponent a, then 5 to the a, or I think, sorry, let me call this k. I think that's what I did in class. So I'll say k and 5 to the k. Then I need to do sort of 6 numbers in a row. So 0, 1, 2, 3, 4, 5. So I sort of go up from 0 to sort of phi of 18 minus 1. So that's why I'm going up to the 5th power. And so the point in being a primitive root exactly says, if I sort of compute these powers, I'm going to hit every element of U18 exactly once. So 5 to the 0, that's 1. 5 to the 1, that's 5. 5 squared, I already computed. That was 25. That gave me 7. Then 5 cubed, I just multiply that by 5. I'm taking mod 18. So I got 17, which is also minus 1. So if I multiply that by 5 again, like now I'm getting minus 5, which is 13. And then 13 is the same as minus 5. So if I multiply that by 5 again, I'm getting minus 25. So minus 7. So that's 11, which I sort of could have just seen in some of the last one has to be the only one you haven't gotten so far. So like, since I knew this was U18, like, and the only thing I hadn't hit yet was 11, of course I was going to get 11 here since this is a primitive root. Good, but okay, so now I have this table sort of that translates powers of 5, that sort of writes down what are the powers of 5, and I can use this when I'm solving these. And when you're doing this kind of problem, you always really want to have this table written down because it makes it very quick. So now if I'm solving x to 11 is congruent to 5 mod 18, well, let me write x is equal to 5 to the, and I can call it whatever, let me call it 5 to the a. So then I'm looking at 5 to the 11a. Let me write this way. So when I'm solving 5a to 11 is congruent to 5 to the 1 mod 18. So here, this part was easy because 5 is just 5 to the 1st power. So I didn't really need my table for that. Good, so I get 5 to the 11a is congruent to 5 to the 1 mod 18. And the point of this method is that when I'm solving this, so here I'm solving this equation, I've reduced it to sort of looking at sort of the exponent of 5 appearing. And then now, because 5 is a primitive root, this is really the same as saying that 11a is congruent to 1 mod 6. And so the reason I get 6 here is because 6 is phi of 18. Good, so if I sort of do that, okay, I mean, so 11 is congruent to 5 mods. So this is the same as 5a is congruent to 1 mod 6 because 11 is congruent to 5. Well, that's minus a is congruent to 1 mod 6. So a is minus 1. Since I didn't sort of compute the minus 1 power, I want to sort of put my power between, so I want this a between 0 and 6. So I want sort of the standard solution. So in other words, a is congruent to 5 mod 6. Okay, so x equals 5 to the 5, because x is 5 to the a. So x is equal to 11 mod 18. Okay, so if you compute 11 to 11 mod 18, you should get 5. We can compute probably 11, and we can probably do this. Let's try. I didn't do it beforehand, so we'll see if we screw up. But in 11 to 11, well, I can sort of use, yeah, I guess this one will actually be kind of hard to do, so maybe I won't do it. But 11 to 11, like, I can reduce that using the sort of phi of 18 is 6. That's the same as 11 to the 5th power. Good. So that's supposed to be 5 mod 18. Yeah, let me not try and do it. Okay, anyway, this is how you do this problem. So maybe you'll be able to check your answer, maybe you won't on the actual exam. So sometimes though, you can sort of just compute, you can actually compute this once you find the answer to check it. Sort of depends on the powers, how practical that is. And you can always do it, but it might take more time than it's worth. But this is how you solve it. I mean, sort of you write x is equal to 5 to the a, then you rewrite this as sort of 5 to the 11a is equal to 5 to the 1 mod 18. That's 11a is equivalent to 1 mod 6, because the exponents have to be equal mod phi of n. So phi of 18 is 6. So that's the same as 5a is equivalent to 1 mod 6, or minus a is equivalent to 1 mod 6. A is minus 1 mod 6, so a is 5 mod 6. So like the point is sort of once you've sort of set it up as just a linear congruence between the exponents, this is really easy to solve, sort of no matter what you get here. And then you find what this power a is. Then you plug back in x, like the thing you actually want is 5 to the a. So here we got a is 5, x is 5 to the 5, and then we went back to our table where we compute that 5 to the 5 is 11. And that's how we got x is 11 mod 18. Okay. So then let's do this other one. So we're looking at 11 to the y's congruent to 7 mod 18. And we do a similar sort of thing here. So we're solving for this exponent y. So we write 11 is 5 to the 5, just using my table. So 11 is 5 to the 5. So y is congruent to 7 is 5 squared. So this is going to 5 to the 2 mod 18. Okay, so we get 5 to the 5y is congruent to 5 squared mod 18. And then this becomes a condition, sort of there's a linear congruence between the exponents. So this becomes, again, just like the other problem, 5y is congruent to 2 mod 6. So again, your congruence mod 18 turns into a linear congruence mod phi of 18. So that's why we're getting the 6 here. So 5y is congruent to 2 mod 6, which is minus y is congruent to 2 mod 6. So y is congruent to minus 2 mod 6. And so y is congruent to 4 mod 6. Okay, and so that's the answer for this one. So y is congruent to 4 mod 6. And well, if you computed 11 to the 4th power mod 18, you should get that. We could probably, again, that one's actually a little bit easier. So you could sort of actually check that by hand. We know how to compute 11 to the 4th power mod 18 using successive squaring. So you could sort of double check this answer using that. Good, but anyway, this is the idea of how you do this problem. So this problem again, you'll be given some number. It'll be some relatively small number. It'll be a low 2-digit number, like 18. You'll have to find a primitive root, so you'll sort of want to write out what are the units. And the first thing to do is always sort of write out what phi of n is, so you know how many you're going to get. That way you sort of make sure you don't make any mistakes. You write out the units, then you start trying them until you find one that gives you a primitive root. You use this criterion so you don't have to compute all the powers in case, like, I mean, okay, and eventually once you have your primitive root, like, you're going to write down this table, so you will want to compute all of the powers and then, but like when you're just checking, you don't want to have to compute all the powers, because like if like the first one isn't a primitive root, you don't want to waste time. You want to just move on to the next one. So you sort of compute these two powers to check it's not a primitive root, and to check if it is a primitive root, and then sort of after you find one that is a primitive root, then you make this table. Once you have this table, you sort of use this sort of like discrete logarithm procedure to solve these types of problems. Okay, so that's sort of an example of what could be going on here. There will only be one congruence on the exam. So here I sort of gave you an example and sort of told you to solve both of these. On the actual exam, actually, let me double check. Sorry, I don't want to give you wrong information. Yeah, on the actual exam, you only have one of these types of problems. So you'll have to, so you won't have to sort of solve both types, but of course you don't know in advance whether it's going to be this type or this type. So make sure you know how to solve either of these. Okay, are there any questions about this problem? How do we get from 5y to minus y? So 5 is minus 1 mod 6. So when we're doing sort of this kind of equation, like we can always replace, like we can replace this 5 with minus 1 because they're congruent mod 6. Did that answer your question? Great. Any other questions? Okay, so moving on then. So the last problem asks you to do something with Diffie-Hellman and or RSA, like the last two exercises on homework 7. Rather than write out, and those are probably pretty fresh in your head since you turned it in last night. So rather than write out a new problem like that, let me just go over the solutions on homework 7. And I'll post the solutions when I post the video, so right after we end class today. So let's see, I have some solutions. Good, so okay, so that was problem 3 and problem 4. So problem 3 was an RSA problem. So I wanted to send part A, I wanted to send the encrypted message number by sort of encoding it 2 letters at a time, and then excuse me, doing using the N is 1517 and E is equal to 7. Okay, so for this part A to transmit it, well, first I break up number into 2 letters, so NU, MB, ER, into 2-letter chunks, and then I encode each letter, each sort of pair of letters, sort of by taking like just the number of the letter, the number of the first letter plus sort of 26 times the number of the second letter. So like 14, this is just like we did in class. So like NU becomes 14 plus 21 times 26. That's because N is the 14th letter and U is the 21st letter. I believe, let me double check again, sorry. I think on the exam, I give you a list. Yeah, on the exam, so you don't have to like write this for yourself. On the exam, I list like A is the first number, B is the second number or second letter, C, like I give you a table with the alphabet and sort of which number it is right at the top of this problem. So sort of whether it's an RSA problem, whether it's a Diffie-Hellman problem, you'll know sort of what letter, what number each letter corresponds to sort of from a table at the top. You won't have to sort of rewrite that table or sort of do it in your head. Good. So we have NU, MB, ER. We translate those into numbers. And then to encrypt it, I sort of take that number I get, and so I'm going to make 3 transmissions. Like to sort of send this message, I have to sort of transmit 3 different numbers, encrypting each of these. So I compute sort of this number. So 560, if I want to transmit that, what I actually send is 560 to the 7th power modulo 1517. So that 7 is sort of the E in my public key, and then N is 1517. So I have to compute 560 to the 7 mod 1517, 65 to the 7 mod 1517, and 473 to the 7 mod 1517. And I compute those. On this exercise, of course, I just did it with Sage because these are pretty big numbers. And I got 1350, 1094, and 1118. And these are the 3 numbers that I transmit in order to send the message number in encrypted using this RSA key. Good. And so that's sort of part A. So this example, and this was just like how you send a message. If someone, like how you send an encrypted message to someone who's published their RSA public key. Of course, on the exam, you won't have Sage, and you won't have Sage, and you won't have a calculator, so it'll be hard. Like, I wouldn't ask you to compute 560 to the 7, for example, mod a 4-digit number, and that would be, I don't think I could do that correctly. So you won't, the computations won't be this complicated. So let me sort of point out 2 things. Like if there's a problem about RSA, then instead of encoding 2 letters at a time, you'll just encode 1 letter at a time. So you're sort of only get a number between like 1 and 26. And then this N will be a lot smaller. Like this N will be, would probably be a high 2-digit or a low 3-digit number. And then E would also sort of be a relatively manageable one, like sort of small, probably not squared, but maybe cubed, maybe 4th power, sort of something that you can do with a relatively small amount of successive squaring computations. So you will sort of have to, like, you should be comfortable like multiplying sort of 2-digit numbers and sort of reducing mod a 3-digit number. But they'll be set up to be like relatively easy computations once you get started with them doing that. So sort of low 2-digit numbers, low 3-digit numbers. And so just be careful when you do the computations, and they should end up being relatively simple if there is an RSA problem on the exam. Okay, good. So that's sort of about sending encrypted messages, and then sort of how do we do the second part. So the second part, I would sort of then compute the number F I would use to decrypt messages, and then verify your answer by decrypting the message you sent me in part A. So good. So well, in RSA, and sort of it works because N is a product of 2 prime numbers. And the point is sort of somehow it's hard to factor N. Here on this one, like you just use Sage to factor N. So we've used Sage and got 1570 is 37 times 41. Once you know that, you can compute phi of N. And then you know that F is just the inverse of E mod phi of N. So here, our F was the inverse of 7 mod 1440. And then I just used Sage to compute that meant F was 823. And then once you sort of verify, you just sort of check that when you decode. So you like 1350 to the 823 recovers 560. So this is what like the person decoding would do. Good. And sort of the point is sort of, it's sort of supposed to, like in actual practice, when you choose these numbers, like you make N really big. And so then it's like even a computer can't factor N. And then sort of there's no way to compute what F is for someone else. Good, but okay, so that's sort of how you do this type of problem. So to break it, I mean, to sort of understand like a problem like this, where I'm saying sort of compute the number F, so somehow like breaking the encryption, what that really means is you sort of factor N, and then sort of once you have the factorization of N, then you can sort of just do the same thing that the person receiving the messages would do when they're setting up their RSA public key. So you compute phi of N, and you compute the inverse of E mod phi of N. So that's sort of how you do this type of problem. So for if this type of problem were on the exam, then I would either give you the factorization of N, or N would be so small that you could sort of compute the factorization just by trying to divide it by a few small prime numbers. I mean, somehow you all, like in RSA, you always know n is going to be a product of two primes. And so you, like, if I just gave you an n and didn't tell you its factorization, it'll be the case that you can sort of, just by trying dividing by a few small numbers, you'll find what one of those primes is, and then you get the factorization. So that's how you do, okay, that goes over this homework RSA problem and sort of how it might change if there were an RSA problem in the exam. Before I move on to the Diffie-Hellman problem from the homework, are there any questions about that? Okay, well, I will move on then to the Diffie-Hellman problem that was on the homework. So when we do Diffie-Hellman, the idea of Diffie-Hellman is you establish a shared secret, and then you use that shared secret to do a shift cipher. Like that's sort of like the most basic, simplest way you can use Diffie-Hellman. So some of the point of Diffie-Hellman is to get the shared secret, and then the shift cipher is just some way to turn that shared secret into sort of like a nice way to encode messages. And so like this problem said, sort of gave you the information and said a shift cipher is established using Diffie-Hellman with p equals 47 and g equals 5. And then the messages, the numbers exchanged to establish the key are 38 and 3. And then you break the encryption by finding, so then the problem asks you to sort of break the encryption by finding what the key is. So finding what the shared secret is, and then using it to decipher the message, ekpitsiv, and so on. Okay, well, when you're doing this, you can sort of, you need to sort of find the information that people use to do it. So like, remember, like one person picked a number A, another person picked a number B, and then so the first person sent 5 to the A, the other person sent 5 to the B, and then they took the number they got and they raised it to the A and B again. So like one of the numbers that was transmitted was 38. And so 38 was sort of 5 to the A, where A was the secret number that one person had. So if you can sort of solve 5 to the A, like if you can solve for A, so if you solve 5 to the A is going to 38 mod 47, then you can sort of break it. And so this is sort of how you can break this kind of problem. So this kind of encoding. So I have to solve this. And well, here I sort of just use Sage to do it. And so I use Sage to compute sort of powers of 5 mod 47 until I got 38. So if there were a Diffie-Hellman problem on here, the modulus would be much smaller, and so that would be easy to compute powers of this thing to sort of reverse engineer and solve like 5 to the A is equivalent to 38 mod 47. Or maybe you'd be given a primitive root so that you knew how to solve this. Good. So that's anyway, this is how you can do it. So just by reverse engineering, sort of computing powers until I find one that gives me 38, that's how I find A. And in this case, you sort of get A is equal to 17. Good. So A is 17. And so that now to get the shared secret, now I can just like behave as the person who sent 38 would. I take this other number 3 I got, and I raise it to the 17. So I raise it to the A, because like once I know what the one person's secret number was, I can just do the same thing they do to get the shared secret. So I get 3 to the 17. That's 2 mod 47. So that means the shared secret was 2, which means sort of whoever sent me this just sort of took the message they wanted to send and they shifted each letter by 2. So if I want to go back and decode this message, I just sort of shift back by 2. So I sort of have to go back 2 letters to decode the message. So E becomes C, Q becomes O, P becomes N, and so on. And if you did this, you got the message, congratulations. Small reward for the effort. Okay, but that's how this works. So the idea is if there's a problem about Diffie-Hellman, or a problem about RSA, in either case, like really you need to understand how the algorithm works well enough that you can sort of both use the algorithm, like you can sort of compute the things that need to be computed, you could sort of transmit a message if you were asked to, but also that you understand well enough that you know what you'd have to do to break it. And then sort of the computations are simple, you can actually do those computations to break the code. And that's sort of a good level of understanding to have. And if you understood these two problems completely, then sort of that's about the right level of understanding to be able to be successful on the exam. Just remember, so this, there will only be, yes, let me go back actually. Well, I guess, are there questions about the Diffie-Hellman problem that was on the homework? Okay, so let me go back to the presentation. So, right, so and make sure you review there. So on the homework and on the exam, there'll just be one. There will either be a Diffie-Hellman problem or an RSA problem. There won't be both in this problem 5. But and they might show up, for example, on the short answer questions. So make sure you're familiar with both. And well, even if you guess which one I'm going to give you, like you might still need the other one on the short answer ones. But so just be familiar with both. And again, so let me just emphasize, like on the homework 7, of course, we use Sage because the computations are too hard to do by hand. The computations will be set up so you can do them by hand. Whatever it is, whatever the question is, it will be set up so you can do by hand. You might have to do some simple like long division with 2 or 3 digit numbers. So just be ready for that, but it's going to work out, like it will work, the numbers will work out pretty simply in the end. So it won't be very complicated when you actually do it. So just don't get scared about sort of doing long division with like a 2 or small 2 or 3 digit number. Okay, good. Are there any questions about problem 5? Okay, well, if there are no questions about problem 5, are there any questions in general about the exam or any of the topics we've covered in class leading up to the exam? So I will give you an uncomfortably long time in case anyone's typing questions. Okay, well, it looks like there are no questions then. Well, thank you for coming, everybody. I will post this video and the notes right after I close the Zoom. After I close the Zoom session, I will also post the homework 7 solutions. Good luck on the exam on Thursday. Sojan will be administering it again. And feel free to email me if you have any questions that I didn't get to today. And I hope you all had a nice spring break and are feeling relaxed and ready for the exam. And I look forward to seeing you next week. Good luck.